Welcome to Radio Frequency Integrated Circuits Design class. This is a lecture on Unit 3. And Unit 3, we have two main topics. One is a brief review on impedance transformation, basically passive impedance transformation. And the second part of Unit 3 is we'll start with RF circuits, which starts from low noise amplifier. So let us start with this impedance transformation technique. So so we will be taking the basics what you have done in your network analysis and even in your microwave. So we'll be taking the help of those things and we'll do this impedance transformation. So this is Unit 3. Yeah. So impedance transformation. So what comes to your mind when you hear about impedance transformation? You can use the chat box. If you have some ideas, you can just put it over there. When you listen to the word impedance transformation, what comes to your mind? Your passive is just added to the impedance transformation. The changing of impedance. Okay. Try to match impedance to reduce power loss. Yes. Changing impedance such that power loss is minimum. Convert L into C and vice versa. Matching. Okay. Yeah. So yeah, matching. Yeah, I think you all are trying to relate with this some kind of impedance matching, right? Yes, matching of impedance to get maximum power transfer. Yes, that is true. Yeah. So the here what we meant by this impedance transformation here is to convert from low impedance. I'll use Z, low impedance, to a high impedance, or vice versa. So either it is a conversion from a low impedance to a higher impedance or from a higher impedance to lower impedance. The idea is actually to provide matching. And if you ask me the question, why do we need matching? Because we know that maximum power transfer is possible when your source impedance is equal to load impedance. That is a basic idea behind this impedance transformation or matching. Now, when you look at RF range, so at RF, at radio frequencies, we generally use passive networks. I'm talking within an IC. So within an integrated circuit at RF frequency, we'll generally use passive networks to transform impedance. Right. So impedance transformation or impedance matching is required because we are looking for actually matching networks. So matching networks can actually give, or if we introduce such sections to make the source impedance equal to load impedance, we can actually give maximum power transfer. So that is a basic idea here. Now, to understand this impedance transformation technique, so in simple ways, yeah, I'll call this as IT. Impedance transformation is IT. So we use passive networks. So when I say passive networks, we'll use either resistors, inductors, or resistors, capacitors. So we use some R, L, C elements to do this impedance transformation. That is what we will study now. So based on this, there are a lot of matching networks available. We will study a few of them and see how transformation or how we can convert from a lower impedance to higher impedance or vice versa. Now, to deal with such things, we need to have some tools with us. One is we need to understand what is quality factor for elements, right? So what comes to your mind when you hear quality factor or Q factor for elements like yeah, what comes to your mind? Any response? frequency requirement. Okay. We have defined the selectivity of a filter in terms of quality factor. If you remember, even in a network analysis, you would have studied about one more definition for this quality factor. 1 by Q frequency selectivity. Yeah, with respect to filters, it is selectivity. And now one more definition we usually give for quality factor. How accurate the value of the device is. Okay, that is coming closer. So quality measure for performance, resonance, frequency range. Yes, I think all of you are relating this with respect to resonance and related stuff, right? Energy stored. Yes, yes, something very close. Yeah, so quality factor is actually a performance factor which we express for energy storing devices. Yeah, energy stored. Yes, it is used for energy storing devices. So this quality factor or Q factor will tell you, this will give you a hint how close to ideal an energy storing devices. So if you have an energy storing device, how close to the ideal is that energy storing device? So that information is given by, yes, Sai Shrikar, it is energy stored to energy lost per cycle. Yes, energy lost is nothing but the energy dissipated. Yeah, we have equations for that, like omega L by R on like R by omega omega C. All those things we will write with respect to the way we configure the circuit. Yeah. So the takeaway point here is the Q factor or quality factor is a performance factor which tells you how close to ideal is an energy storing devices. Say, let us start with a capacitor. So we know that a capacitor is an energy storing device, right? So let me write in like this, a capacitor. So an ideal capacitor, an ideal cap, it is an energy storing device. So, or I can say that an ideal capacitor will not dissipate any energy. So dissipates no energy. Right. So since an ideal capacitor is not dissipating an energy, we often express this, the Q factor of an ideal capacitor, as infinity. So if the capacitor is not dissipating any energy, we will express the Q factor as infinity. Now the question is, under what condition, or why are we writing it as an ideal capacitor dissipates no energy? So what is the possibility whether a capacitor will dissipate energy? Yes, there can be some losses in capacitors if there are some parasitic resistance associated with it. So we generally express that in terms of series element or in terms of parallel element. Yes, yes, Rakshit, R component. Yes. So say if there is a series resistance, RS is there with the capacitor C, then if there is a resistance associated with the capacitor, then the resistor is a dissipative element and that lead to the dissipation of energy, right? So in an ideal capacitor there is no dissipation of energy, so we have taken the Q as infinity. But now in a capacitor, in a real capacitor, when there is some resistance element, and if I am considering that resistance element in series to the capacitor, this Q, whatever we have written before this Q, will definitely reduce, or Q cannot be infinity, right? So that is what we define Q factor as. It will show how close to ideal and energy storing devices. So this is an ideal capacitor where we wrote Q as infinity. Now if I have a capacitor and a series resistance along with that, say I call this as C and this as, since it is series resistance, I call it as RS. Now how to define the Q factor of this? So I should say that when this RS is 0, the Q factor will be infinity, and when in presence of RS, your Q factor will reduce. So we write this Q factor as the desired component reactance, that is nothing but 1 by omega C, that is a reactance of the energy storing device to the value of the dissipating dissipating component. So Q factor is often expressed as 1 by omega c, or the reactance of the energy storing element to the dissipating. Series resistance also refers to the leakage current in between capacitor plates. Is there a question? Okay, no, Nikhil, it is not. It is not the leakage component. Probably you are, if you are referring to the dielectric leakage. No, the series resistance can be considered as a parasitic resistance comes along with the capacitor. Especially, yeah, that is true everywhere, especially in integrated circuit. It can be whenever we use something called as min capacitor or mom capacitor, metal oxide metal, or metal insulator metal. We come across these kind of parasitic resistance. Now, one thing you can see here, so this is actually the desired component, right? This is what is a desired component, or the capacitor is an energy storing device, but this RS is something undesired. Even though we call it as undesired, we cannot get rid of this component, because this will be part of whatever elements we fabricate, or whatever elements which comes, right? So this is a parasitic component. Now you can see that when your RS is equal to 0, your resistance will not be there, and that will actually give you a Q factor of infinity, right? When RS is 0, there is no resistance. It is same as the ideal, and the Q factor will remain as infinity. So since this Q factor is defined along with the series resistance, we give a subscript Qs here, where Qs is equal to 1 by omega c into Rs. Right. Now, in most of the cases, even though the resistance is seen in series with the capacitance, for calculation, or for whenever we deal with circuits, it is easy, or it is better that if we model this resistive loss in terms of a parallel resistance. So let us see what happens if I am modeling this resistive loss when it is modeled by parallel resistance Rp. I call this as Rp. So my circuit will be like this. So this is capacitor. Ideally, this will not dissipate any energy. Now, if I am considering a resistance in parallel to this, so this is C and this is Rp in parallel to this. Here also we have to define Q factor. So I'll define Q factor here as so what I want here is Q factor should give me an idea about the closeness of the capacitor to its ideal value. Now, in the absence of Q factor, the capacitance, in the absence of resistance, the Q factor should be infinity, right? So the formula, or the way to express Q factor is, we'll express Q factor as the parallel resistance Rp divided by 1 by C omega. So what happens in the absence of Rp? So Rp will be absent if Rp is equal to infinity, right? Rp cannot be short. Rp when I say Rp is not there, Rp should be infinity. So when your Rp is infinity, that leads to Q factor also an infinity value, right? So this is how we express Q factor for a parallel Rp. So for this reason, we define this Q factor as Qp, which is for a parallel RC network, right? So I'll just write it here. Q for a series RC is equal to 1 by C omega into Rs, and Q for parallel RC network is equal to C omega into Rp, right? So this is true. These two equations, these two can be used for RC networks. So we have considered the energy storing device of a capacitor. Similarly, we can write the same thing for an inductor also. So if I write that here, so if there is an inductor, the ideal Q factor should be infinity. Now, when I consider a series resistance here, so this is L and this is Rs. Now, if I write the Q factor for this, I hope you are with me. So the Q factor will be L omega by Rs. When your Rs is 0, your Q factor will be infinity. Similarly, if I consider this resistance as a parallel component, this is Rp and this is L. I can write this Qp as Rp by L omega. Here, when your Rp is to make the circuit free from Rp, Rp should be open, Rp is infinity, then your Q factor will be infinity. So these equations are valid for RL networks. So how we express Q factor is very much required to understand this IT, impedance transformation methods. I hope this is clear. If you have questions, you can put in the chat box. Now, okay. Now let us see. Let us consider both the series section, series RC, and a parallel RC section. Let us consider either RC or RL network, and let us see for which values these two networks, which values this parallel and series networks are equal. I don't know. Are you following me? So what I'm doing is I'm just trying out this series to parallel conversion. So series to parallel conversion. The idea here is what I'm trying to do here is I have a series RC circuit. Now I'm trying to find the equivalent parallel RC. So if you have, because I told you that, yeah. So even though resistance appear in series with capacitor, in circuits for analysis, for better analysis, we always consider the resistance as a parallel component. So that means in some cases we may need to convert the series RC into parallel RC or series RL into parallel RL. So how do we perform that conversion is what we are going to discuss now. Okay. Now there are questions. Will there be any way to calculate the Q factor of an RLC circuit? Yes, we can calculate. Is there any mathematical proof for which one? For what you're asking? Yeah.
Sir, you mentioned that for R, when the R is in parallel, like we took the initial conditions that that Q should be infinity when RP is infinity, and hence we reduced this equation for the quality factor.
Yes.
Is there any mathematical way of getting?
Yeah. Yeah, definitely. The equations what I have written is mathematically derived. To make it very short, I have explained in this way. So mathematical proofs are there. I hope you would have done this in resonance of your network analysis. Is that done?
I have to go and I have to check again, sir.
Yeah. Please check again because all these derivations are available.
Okay, sir.
Okay, yeah. Anirudh, your question is, yeah, we can actually calculate for an RLC, yes. Yeah. Now, okay, let me go with the series to parallel conversion. So what we are doing here is we have a series RC. So let me call this as RS and this as C. Now I want to know at what values or when can I say that a series RC component is equal to a parallel RC. So this is your parallel RC network. Right. So here I'll use this RP. Now to avoid confusion, for the series capacitance I'll put it as CS, and for the parallel capacitance I'll put as CP, and let us see whether the CS and CP are equal or not. Right. So what I'm going to do now is I'm trying to convert a series RC to parallel RC, and thereby finding the relation between RS, RP and CS and CP. Right. So if you have a series RC element and if you're asked to convert that into a parallel RC, If you know the relation between this RS, RP, and CS and CP, of course, it is in terms of Q factor. That will be easy. That is what that analysis is what I'm going to do now, right? So, can you tell me how to start this analysis, how to do this conversion, or how to get the equivalent values of RS and RP when you have two networks, one is series and one is parallel, and to find at what values they are equal, or the relation between the elements. Am I audible?
Yes, sir.
Yeah. If you have any idea, you can put in the chat box. Assume one constant frequency. Okay, we will find impedance for both networks and equate. Yes, yes, that is the usual way we take. Currents and voltages should be the same. Okay, current, yes. Okay, let us see that. Yeah, so the common technique what we use is we'll try to equate the impedance first. So we will be equating the impedances. So the impedance here is this is RS. The series impedance is RS plus 1 by SCS is series impedance. Now the parallel impedance is RP parallel 1 by SCP. Right. So I'll write it as RP into 1 by SCP. If my voice is breaking or if my voice is not there, please let me know. RP into 1 by SCP divided by RP plus 1 by SCP. So what we are trying to do is we are actually equating the impedances here, right? So you can solve along with me. 1 plus SRS CS divided by SCS is equal to, to do here, it is RP divided by 1 plus SRP into CP. Right, or further if you multiply, I can write it as 1 plus SRSCS into 1 plus SRPCP. I'm doing cross multiplication equal to SRP into CS, right? Or if I further multiply this, it is 1 plus SRSCS plus SRPCP plus S square into RSCS RPCP equal to SRP into CS. Now, to equate the real and imaginary part, I'll substitute S as j omega, and for that, I'll rewrite these equations. So it is 1 plus j omega into RSCS plus j omega into RPCP. S square is minus omega square RS CS RP CP. So again equal to j omega into RP CS. Right. Now, so we have equated these two. Now I'll take out the real components first. So the real components from this is the real part. I'm separating the real part. Real part is 1 minus omega square into RSCS RPCP equal to 0, right? Or I can write 1 is equal to omega square RSCS RP and CP, and I'll put this as equation number 1. So this I got by equating the impedance, and I have taken the real part from that. Now if I take the imaginary part, I'm taking the imaginary from this, I can write it as RSCS plus RPCP minus, sorry, is equal to RPCS, right? So j omega will be cancelled, so which is the imaginary part. So I equated a real part and imaginary part. Now, now what I'll do here is, so if you look at this equation is, yeah, 1 is equal to omega square RSCS RPCP. So what does this implies? omega square RSCS RPCP is equal to 1, which means the Q factor of series network is equal to Q factor of parallel network, because we have seen that the Q factor of series is 1 by 1 by omega RC, and the parallel is omega RC. You can see here that omega square RC is equal to 1. That means your QS is equal to QP. That is the first inference from the first equation. Now, from first equation, what I will do is, first equation from first equation I'll take the value of RPCP, which is equal to 1 by omega square into RSCS, right? Now from the second equation, hello, yeah,
Yes, sir.
right, okay, sorry. Okay, so here 1 by RPCP is equal to, yeah, RSCS minus RPCS minus RSCS. So this from these two equations, from let me just write this as equation 3 and equation 4. So I can actually equate 3 and 4. That will give me this equation: 1 by omega square RSCS is equal to RPCS minus RSCS, right? Or I can write here that RPCS is equal to, so what I'm doing with this analysis is I'm actually coming to the values of RSCS, RP and CP, the relation. So let this be here. RPCS value is obtained as RSCS plus 1 by omega square RSCS, right? Now, in a similar way, what I have done here is, similarly, if I write the equation for, okay, let me write this for RSCS. So from the same equation number 1, if I write for RSCS, it is equal to 1 by omega square into RPCP, right? So this is equation number 5, and from this is again from equation number 1, and from equation number 2, if I write for RSCS, I can write RSCS as RPCS minus RPCP. Now this is equation number 6, and now when I equate this 5 and 6, here I get 1 by omega square RPCP, which is equal to RPCS minus RPCP, right? So from this I will get RPCS as 1 by omega square RPCP plus RPCP. I hope you guys are following this derivation part. Now I have two equations with me. So this is equation number 7 and this is equation number 8. Now from this equation number 7, if I divide both sides with the capacitance value of CS, I can write this equation number 7 as, the 7 will give me the value of RP, Rp is equal to Rs plus 1 by omega square into Rs into Cs square. Right, that is from equation number 7. Similarly, from equation number 8, if I divide by Rp on both sides, I can get the equation for Cs, right? Yeah, I can write for Cs is equal to 1 by omega square Rp square Cp square plus Cp, right? I hope you are following. Now I'll just bring in the Q factor into picture. So I know that a series Q factor for an RC element is 1 by omega into Rs into Cs. And okay, so if I substitute, or if I look at equation number 7, so this I am giving to this, I am substituting Qs in equation number 7. So in place of 1 by omega Rs Cs square, I will write Qs. So if I insert Qs, one Rs is missing, so that I have to actually give to the numerator, or I can write it as Rp is equal to Rs plus, if I want to write denominator, so 1 by omega Rs Cs is Qs. So 1 by omega Rs Cs the whole square is Qs square. So if I want to write this as Qs square, I have to substitute or put an Rs also there, because one Rs is missing in the denominator. Or I can write Rp is equal to Rs into Qs square plus 1. Right. So this is the value of Rp in terms of Rs. Right. Similarly, if I do the other operation, that is by substituting Qp. So what is Qp value? Qp is equal to Rp Cp into omega. All right. Oh, I didn't see the questions. Why Cp square? In which point Cp square?
Sir, equation 8, sir.
Okay. Equation 8 I have written from, no, oh, I already used equation 7 and 8.
It implies
Yeah.
CS is equal to.
Yeah. So what I did is I am bringing this, oh, okay. It is CSCP, right? All right. Yeah. That is from equation number 7 again.
Sir, in the next slide, where you have written the expression for CS,
Okay.
it will be 1 by omega square Rp square Cp. Sir, it won't have a Cp square term in
Oh,
the
yeah.
denominator.
Yes. Very good. Okay. CP. Okay. Yeah. Right. CP plus CP. This is right, no? CP square, yes, in RSCS equal RPCP, since in
Yes, sir.
7 and 8 they are interchangeable. Akshay Narayan, yeah, it is interchangeable, yes. I don't know, you are asking in.
Yes, sir, in equation 7 and 8. Since LHS is equal RPCS and RPCS both in 7 and 8. So if we equate both of them, RSCS would be equal to RPCP. That's why
Yeah,
I asked whether they are equal.
yeah. When we equate these two, yes, that is true, correct.
Yeah, okay, sir. Okay, sir.
Yeah. Okay. Now, okay, I think I have made a mistake here, and that is rectified now. Now I am taking the equation for QP. Rakshak, I didn't get equation 8. If you are referring to the same mistake what I have done, yes, I have corrected it. Yeah. So QP is RP Cp into omega, and so if I write equation number 8 here, so if I substitute this in equation number 8, I can write it as Cs is equal to, yeah. So Cp, yeah, right. Cp is missing. So I should write 1 by omega square. So omega square, 1 by omega square Rp square, Cp square is Qp, right? So this should be written as, Yeah, so QP is this. Yeah, so here I'll bring in that this is equal to QS is equal to 1 by RS CS into omega. Now I can write this CS as CP by QS square plus CP, or I can write CP here as CS into QS square divided
So
by
that'll be QP square, sir.
which one?
CP by QP square, sir.
That is one. What I have taken here
Both,
is,
both are equal.
yeah, both RP CP omega is
Okay.
equal to, yeah, that condition I have taken to express both in terms of the series Q factor element. So this is CP value, right? Now one more thing we can do here. Now say if your QS is very large compared to 1, when I say very large, say Q is having a value of say some 4 or 3, so 3 square is 9. So 9 is large when compared to 1, right? So in such case, this can be approximated as RP can be written as RS into QS square. This is true only when your QS is large, not comparable when QS is large. If your QS is somewhere around 1 point or close to 2, then this approximation cannot be done. So you can take that if your Q is greater than 3, Q square is 9 or something like that. That is the case when you have RC or RL circuits on IC and when you measure the Q factor. Similarly, here also you can do the assumption 1 can be neglected if your Q is large, and in that case your CP is actually equal to CS. Now this is true only when QS is large compared to 1, right? So so we have come to a conclusion here that we started with series to parallel conversion and we arrived at the relation between the series and parallel resistance elements and series and parallel capacitance element. Okay, CP by QP square. Okay, under this, if it is you are telling to me, please clarify. I didn't get that. Okay, so what we have done here is series to parallel conversion. If you look at the in series to parallel conversion, what happened is this conversion actually retained, series to parallel conversion retains the capacitance value, again under the condition that Q is larger compared to 1, and that will be true in most of the cases. So retains the capacitance value but raises the resistance value, the resistance value by a factor of QS square. So whenever we want to do conversion between series to parallel, what we have to do is we can retain the capacitance value, but Andrew, yeah, we can retain the capacitance value, but the resistance value should be raised by a value of Q square, right? So maybe this derivation or this will not give you much idea. Let us take one simple example and see how this is useful or how we can actually apply these techniques to convert resistance from lower to higher or from higher to lower. So we'll start with a very simple technique. So I'll call this as basic matching network. So what we have discussed now are the ways to convert from series to parallel. Now we'll apply that in a basic matching network. So this can be, when I say matching network, this can be a conversion from a higher resistance to a lower value, or from a lower resistance to higher value. We'll see both methods. So how to convert from higher to lower and from lower to higher, right? Okay. Yeah, so if it is from lower to higher, we call it as upward impedance transformation, and if it is from higher to lower, sorry, higher to lower, it is downward impedance transformation, we'll say. Okay, so let us take one, let us look at one scenario. There are different matching networks available. Let us study one of such kind. say we have a resistance. The resistance value is RL. The value of this resistance is RL. Now, I want to convert this resistance to a lower value. So, I'm looking for a lower resistance value. So, what alteration can be done, or what kind of network can I attach to this to convert this resistance to a lower value network, right? A lower resistance value, that is the idea. So, impedance RL is available and I want to convert this into a resistance, another resistance value. So, what I'm telling here is there are different kinds of matching networks, and this is one of such kind. So, what I'll do first is I'll add a capacitance in parallel to this resistance RL, and I'll call this capacitance as C1. Right. Now, why I'm adding this capacitance is, so I'll state it here. C1 capacitance is actually used, or it is actually C1 is converting RL to a lower value, to a lower value resistance. Say that resistance, let me call some value RS. So RL is the present resistance value. I want to convert that resistance to a lower resistance. I am calling it as RS, and C1 is actually used for that conversion. Now, if I'm adding a C1 element, so what I want is a pure resistance. Now, if I added a C1 element, that will bring in some kind of reactance into the network. Now, I need to cancel that reactance, right? So, in order to cancel the reactance, the ideal way is actually to add an inductor, here to the network. So, I added an inductor in series, and I'm calling it as L1, right? So, that is giving me a structure, something here, and this is L1. So, why this inductance is added? This inductance L1 is added to cancel the equivalent series capacitance. Yeah, Saurabh, your question is, we use a capacitor because of the frequency dependence. All right, so I'm not very clear about that question. Why I used a capacitor is what you are asking. Then the answer is, we need to convert, or we need to transform the resistance into some lower value. So for that, I need to use some energy storing elements, right? So, or we are discussing actually how we can transform impedance using passive networks, passive elements. So I can use a inductance, or I can use why can't we place a parallel resistance? Okay, so how will you place a parallel resistance and transform the impedance? I didn't get that.
Sir, like from what I understood, you're just trying to reduce the impedance seen. Currently, it's RL. So if you placed another resistant parallel, even if they're equal, the impedance would be RL by 2.
Oh, okay, okay. Then I think now Saurabh's question is valid. Yeah, it is because of frequency dependence, because we will be designing circuit, say for some at some particular frequency. Now, I need to make sure that, yeah, there should be some tunability, or there should be some possibility with us to tune with the frequency also. So, adding a resistance in parallel, or adding a resistance in series, because yeah, how will I explain that?
It will provide the same impedance for all frequencies.
Yeah, there is no frequency dependence, first of all,
Yes,
and the second thing is, uh, yeah, maybe let me take one example on how we will work on these kind of resistance. Maybe that will give you a little more clarity.
sure, sir.
Yeah, because most of the time when we use this matching network, no, say you'll be having two circuits, and you are finding that there is some impedance mismatch between both. So there, adding one more resistance in parallel may or may not affect the signal which is getting propagated also. Right. So, sir, there are a lot of things to consider. That is why we have this specific set of networks called as matching networks. If the condition is you just have a resistance, and if you want to increase the resistance, you can actually add a series resistance. right?
Yes, sir.
Now we are actually looking for we have cascaded stages. Now we have to think this in the for an entire RF transceiver chain. You have LNA, you have filters, you have mixers. Now the impedances of the output impedance of one should be matched to the input impedance of next, right? So
Yes.
there, that is one thing. The second, one more thing what you can understand is, if I add an extra resistive element, that will definitely bring in more noise to the circuit, right?
Yes, sir.
Especially we can when we talk or when we consider more about noise figure, we cannot bring in just a resistance like that. I hope it is clarified, Siddharth.
Yes, sir. Sir,
Yeah.
just one last thing. Sir, L1 is added to cancel the equivalent series capacitance.
L1 is added to cancel equivalent. Oh, I wrote it as series capacitance. Yeah. So why I wrote it as equivalent series capacitance is because now you have an RC in parallel. Right.
Yes.
Okay. Okay. So what I'll do is I added a capacitance C1. Now I have RC network. There is a parallel RC. Now what I'll do is I'll actually convert this into series, and then there comes a series capacitance, and now this inductance is added to cancel that series capacitance.
Yes, sir. So like when we look at it from a network point of view, it's like saying we won't have any J component in the impedance.
In the yes, our
Then how
intention is
would it?
actually to cancel the imaginary part, or we will choose the inductance in such a way that we will derive the relationship between this inductance and the capacitance, and we'll make sure that inductance is put in such a way that the reactive components will be equal to 0.
So then how will it become frequency selective? Because we just removed the J part, which
Okay, all right. Yeah, I understand. So let me complete this part, and that will, I think that will definitely give clarity.
okay, sir.
Clarity. Yeah. So because the Q factor plays an important role here actually in this conversion. Now your Q factor, you can express Q factor either in terms of C. It is for a capacitive element or for an inductive element. Right. So that is where this frequency comes into picture. Definitely. Yeah. Let me complete this, and this with the conversion. Say for I can take up some examples and explain to you how this conversion is actually happening. Okay. Is that okay?
Yes, sir.
Yeah, I'll clarify that. Yeah, since anyway time is not there, so we'll continue with this with in the next class, not tomorrow. I think day after tomorrow we'll do with this matching network, and from this matching networks onwards, we'll again go back to our cadence simulation. Right, so we will see the simulations in the cadence software also. One minute.